I have an interesting thing to talk about for astronomy news today. This topic is relatively complex, so I'm going to do my best to explain it in the simplest terms I possibly can, but this is brand new stuff that somebody's doing for their PhD level research. This is pretty cutting edge stuff. Some of the articles I've read so far, they're saying that this is like prolific. I don't know if I'm willing to go that far until we see some more results. It's a lot of new stuff, like very interesting things that we could use to learn quite a bit about the universe. So I think it's really interesting. So let's just take it from the top. Colliding neutron stars provide a new way to measure the expansion of the universe. This headline is not news. We've known that we've been able to use this methodology to measure the expansion of the universe for a while. We just didn't know how to do it. Let's start with what a neutron star is. What a neutron star is it is a big star, or I guess it's actually kind of small, but it is a very heavy star comprised of neutron star material. Now, a neutron star, oddly enough, is not necessarily made of neutrons. It is made up of neutral material, and the reason it's neutral is that this star is so massive, not in terms of size, but in terms of actual mass, that the gravitational force has caused it to collapse so strongly that the electrons that would normally orbit around a positive nucleus have been forced into that nucleus, and combined with the protons to make neutrons. Now, the reason that we don't say it's comprised of neutrons and we say neutron star material is that it's not just neutrons floating around. These things have a very strong magnetic field, and you might question, well, how can you have a magnetic field if you don't have a charge? Turns out that when you have this very strange matter, it causes the neutrons to break down even further beyond just being a neutron. So a neutron is made up of quarks, and those quarks end up turning into this soup. And these quarks each have a charge. The only reason a neutron is neutral is because it cancels the positive and the negative charges from the quarks. When you take a neutron star and you have another neutron star, if they both come in and they orbit each other and they eventually collide, those two neutron stars form another type of nova. This particular type of nova is called a kilonova. And a kilonova is different from a supernova and different from a regular nova. And we are pretty confident in saying that a huge majority of the heavier elements, so, your gold, your platinum, that kind of stuff, all of those came from these types of kilonova explosions. And we have observed these before. In fact, a kilonova explosion, a binary neutron star merger, was one of the first things that we ever used to measure gravitational waves, which is really cool. These two neutron stars coming in together will provide a very large explosion that's very easy to measure. And the question was, well, can we use these to measure a distance? Is there a way that we can say we know it's going to be this bright if it was this far away, and then use that to figure out if it's half as bright, how far away is it? That's the question, because we do that already. We do that with type 2 supernovae, where we're able to say a type 2 supernova is about this bright, and if it's 4 times as far away, it's about twice as dim. So can we do that with these? And the biggest question has been, is it spherically symmetric? And that matters a lot. If we have a spherically symmetric process, then we're able to say that no matter what direction we're looking at it from, if it's 4 times as far away, it'll be half the brightness because it's the inverse square law. If it's not spherically symmetric, like a lot of things in the universe are, it matters what direction we're observing it at. If we're looking at something like, a blazar, a black hole with a jet pointing towards us, it's going to look significantly brighter than it would from any other angle while looking down the barrel of the blazar. So we would need to know the orientation in the sky of whatever object we're looking at in order to get an accurate measurement and an accurate distance from that. Let's talk about the problem that this is trying to solve to sort of work our way up to why this is important. The problem this is trying to solve is something I've talked about before. There is a concept in cosmology that explains the expansion of the universe. It's called the Hubble constant. Say you had a balloon, right? And you put dots on the surface of the balloon. As you blow the balloon up, all of those dots get further away from each other independently. There's no center dot that doesn't move. All of the dots feel like they're in the center of their own expansion. So if we on Earth look in any direction, it looks to us that the universe is expanding. We're not in the center. There is no center. No matter what direction we look, everything is expanding away from us because everything's expanding away from each other. The individual space between the objects is what's expanding. The objects aren't running away from us. It's the space in between them that's expanding. And we know this, we've confirmed this a million different ways. We know it's a thing that's happening. The question is, how fast is it happening? And we have a few ways to figure this out. I talked about the cosmic ladder idea a few times back. This is how we measure distances for things that are beyond our galaxy, or even within our galaxy. The question always comes up for astronomy, and my father used to ask me this question all the time, and it was a point of contention that I explained it a million times, and it never really stuck. And I didn't explain it very well back then. I was still a student. What we are able to do is is we are able to use effectively a ladder system. So if something's very close to us, we can take geometric measurements of it. We as a planet are orbiting the sun. In the springtime, we're over here. In the wintertime, we're over here. And if we can measure what's called the parallax, how a star were to shift on the sky compared to further away objects, we could estimate, or in some cases very accurately determine, how far away that object is using stellar parallax. That's the first rung of this ladder. The next rung of this ladder is something we discussed. It's Cepheids, and these are stars that will kind of blink, so they will pulsate as they grow in size and shrink in size and grow in size and shrink in size, and thus change their luminosity over time. And there are some Cepheids that are close enough that we can measure them through both methods. We know how far they are away because they're a Cepheid, and we know how bright Cepheids are dependent on their periodicity, and they're close enough that we can measure with geometry. So we can calibrate the second rung of the ladder to the first rung of the ladder, and then so on and so forth. So we can use Cepheids and type 1a supernovae that are close together to calibrate that rung, and then use supernovae and a thing called redshift to go even further beyond that. And we can do this effectively to measure distances to objects, and from that, and knowing how fast they move, figure out this expansion rate of the universe. It's more complicated than that, but that's the gist of it. And when we do that, we measure the Hubble constant, which is telling us how fast something moves for every unit of distance it is between the observer, us, and it. If something is twice as far away, it's expanding twice as fast because there's twice as much space in between, and every piece of space is expanding. Now, when we do that, we find that two of our major methods, one is this direct observation and the other is through the cosmic microwave background radiation, they don't agree. I've shown this plot before too, but this shows us measurements of h0, which is the Hubble constant, in the late universe do not line up with the early universe estimations. So late here means things that are close to us, early means things that are far away from us. Back when we first did some of these estimations, each of these different values that we had back in the day, they did line up within their respective uncertainties. Now we're so good at it that the uncertainties have shrunk, and we know for sure, at least we're pretty damn sure, that they are not the same. These early values of about 67 do not line up with some of the late measurements, which are like 73, 72 range. I mean, look at these error bars, right? These are tiny little error bars. There's no way these are going to line up with something like these. So something's up. This is called the Hubble tension. And one of the biggest questions is, can we resolve this Hubble tension? Is there a way for us to say, okay, yes, these are different, but here's why? Or to get another measurement that actually shows us that maybe one of these two methods was wrong. Also, just a fun fact, a bit of a side tangent, there are some theories as to how this might actually work, and by theories I mean hypotheses, not scientific theories. Here are the early measurements, early universe measurements, here are the late universe measurements, all plotted on the same axis. So we're looking at the Hubble constant. I don't think the y-axis says anything, I think it's just there for clarity, just to separate them. But these are all indicators of different ways that it's possible that the early universe may have differed from the late universe. So some of the ideas here, and I'm not going to go into them very much, this is early dark energy. This is saying there was more or less dark energy back in the early universe than there is now. This is dark matter neutrino interactions. This is something we think does not happen in the late universe, but may have happened in the early universe. The important thing is that there are some new physics that we could think about that could put everything within the range of late and early measurements lining up to their uncertainty values. In any case, we need to first understand if these two are different because of the methodology, or are these two different because of new physics, or are these two not actually different? All of these are open questions. So where do the colliding neutron stars come in? Well, like I said before, we know what kilonova look like, and if we know how bright they are, and we observe one, and we get detailed measurements, we could then work backwards to say, okay, if it was this bright at this distance, then we know if it's this brightness, it must be this other distance away. And that only works if it's spherically symmetric, which we know it is, or we know the orientation, but it's spherically symmetric, so we don't care. And if we can accurately determine how bright the thing should actually be. What this paper does, and this is, like I said, a very complicated paper. I'm not going to go over too much of this paper because it gets very crazy very quickly, but there is one thing that I want to show you. So just to kind of show you what's going on, this is what he was working on. This is a very theory-driven paper. But what we're looking at is down here. Ignore all of this. Oh, okay, I can't do that. Can I draw on this? I can. Ignore this, this, and this. We're just looking at this right here. And this right here is already complicated enough, but I'm going to break it down for you the same way that I would break the same looking equation down to all of the students I used to teach in optics. 4 and pi are constants. Here's another pi, that's a constant. This is a distance. It's not constant, but it is telling us something about the shape of the thing that we're looking at, so it's constant for the particular case that we're looking at. So if we're looking at a particular kilonova, R would be the same for that kilonova as an exact copy of it. It's not a variable. This right here is a relativistic correction. Einstein's theory of relativity tells us that as things start to move fast, time and space start to act very strangely. It's a very cool concept, and we might talk about it someday. But effectively, this is just telling us that there is a correction that's a function of the speed of the thing and the wavelength that we're looking at. That's all this is. So this has nothing to do with anything other than the actual speed of the object and the wavelength we're looking at. In other words, for a given speed, like every object would have, and a given wavelength that we're looking at, which we can always calibrate for, that function is more or less constant. Which leaves us with only one more part, this b lambda t observed. What this is this is the actual spectral luminosity of the object. And effectively, what this tells us is that the only thing that changes, or the only thing that changes the luminosity, is the temperature of the object. That's it. And since we were able to prove that, or I should say since this gentleman was able to prove that, we know that we can now actually take observations and fit them to effectively modified black bodies, which is a topic in its own front. But this is huge. This means that we actually have all of the tools that we currently need to measure distances with this method. It's an independent, novel method that we can use to measure astronomical distances, which is huge. We have the whole distance ladder. This is now a new, independent from the ladder method. So if there is something wrong with this ladder that we've been using that we didn't account for, this has nothing to do with the ladder. It's its own methodology, completely separate, which is very, very cool. The only other thing I want to show you is this plot here. This black dotted line right here, that is a black body with that correction that was shown up there. So this dotted red line is a normal black body, and this little dip right here accounts for those corrections that I showed you above. All of this gray stuff in the background, that's the actual data from a kilonova explosion that we have observed. And it lines up perfectly, which means we now have a model that only depends on the temperature for these types of explosions. So we can just fit to that, and we can find the luminosity, which is effectively what this axis right here is. And voila! We know how far away it is because we know how bright something like this should be based on observations. And we have a completely unique method to finding astronomical distances. This is incredibly useful because one of the best ways that we can resolve this issue. Astronomers are concerned that there might be an issue with how we constructed our distance ladder, which could give us huge issues on this front. And since this whole thing has nothing to do with the distance ladder, we don't have that problem. So we'll see where this goes. This was literally published